today.
Good morning, everyone. Welcome to the morning session. And our first speaker will be Professor Micheal Tobar. Micheal, are you around?
Yes, I'm here. I'll share screen then.
Okay. So you have 25 minutes, and then I will let you know 5 minutes before the end.
Does this look fine?
Yes.
Okay, good. Okay, so the title of the talk is Bulk Acoustic Wave High Frequency Gravity Wave Detectors, which is a resonant mass detector. So currently Will, who is online now, is a PhD student working on the project and building the new version of the experiment. The staff members is myself and Eugene were, when I was a student and he was a postdoc, worked on the resonant bar here at UWA. We have a long history of working together. And Maxim Gorachev is now a staff member here, and he did his PhD on quartz Bohr resonators. So we were, the three of us all contributed to this in a very enthusiastic way. And then I have to mention Axion Heng, who as a postdoc, I was his supervisor here at UWA, who worked on the data analysis on the resonant bar detector. And we've been friends for a while, and we used to play soccer together a lot until he went off overseas, and he is now a professor in Glasgow and working on LIGO and various other gravity waves. And then I must mention Serge Gayot, a professor at Franche Comté University. This technology came from his lab, and Maxime did a PhD under him on this technology. And I first saw Maxime at a frequency control conference when he was talking on this technology. And as he was presenting this low temperature properties of these quartz, I was in the audience emailing Serge, who I knew quite well, proposing a collaboration, which has led to all this work and led to Maxime coming here. And it was one of the last talks of the conference, and I never got to speak to him at the conference because by the time I went out to try and find him, he had nicked off. And then the next time I saw him was in France. And now he's a staff here in Australia. So these are all good friends, and enjoyed doing this project with them. Our team here at UWA with the Quantum Technology and Dark Matter Research Lab, we are part of 2 centers of excellence in Australia, Engineered Quantum Systems and Dark Matter Particle Physics. We have a few postdocs and lots of students and a technician, and we have a lot of different equipment. There's our webpage. You can go on there and do a virtual tour and see all the equipment. Just part of we have this quantum systems laboratory with 2 Blue Force fridges and lots of vector network analyzers and lots of equipment, some optics. This is Organ, our dark matter experiment. It's an Axion detection experiment that's currently running and taking data in a certain above 15 gigahertz. This is our cryogenic sapphire oscillator lab, which is where we started from, and we're still building these very low noise oscillators. So the outline of this presentation is that I will introduce a technology at UWA that we use to detect high frequency gravity waves. I will show some Axion technology at UWA that could be used for these experiments that we've been talking about. And our technology, which could be used for resonant mass type gravitational wave detection. But first, I'll give a brief history and the principle of operation of what I used to call the nearly extinct resonant mass detector, bars and spheres, which I did my PhD on. And now there's a sort of a renaissance for these high frequency gravity waves, which is nice to see. And then I'll talk about the piezoelectric bulk acoustic wave detector, which we proposed in 2014. I was in China and I was talking to a member of LIGO. He wanted to know the technology we had, and he said, "Oh, that is probably sensitive to gravity waves." I go, "Oh yeah." Then I came back and Maxim and I worked on this and worked it out. It was very much fun. And now since 2014, we eventually got a grant, and we've been going along very slowly And finally, we got the first run. We had it running, and then we didn't really have many students to look at the data. And finally, Will came along, and Siong was out visiting his parents in Perth, and we got to analysing the data. Then at the end, I'll introduce our future multi-bore detector, which is currently under development and will be operational, if not this year, next year. So first, our inverse, which I say GE technology, because I don't want to say the whole name, at UWA is our Axion type technology. We have the organ detector, which is, the acronym was Oscillating Resonator Group Axion Experiment, and it uses a TM01 mode with a single tuning rod for the first one. Here is an example. It's a small one because it's up around 15 gigahertz. There's a photo of it. Uses a hemp amplifier, 15 to 16 gigahertz, and we've got data already. We've put limits on Axions for better than ALP cogenesis up at this frequency. We're testing these, so this is what we're testing at the moment. Here is our tuning curves. And as I said, we've already got the data here, and we've seen the preliminary results, and we're taking this rest of this data at the moment. We also have this Axion experiment, which is called an AC heloscope and has 2 modes in 1 cavity, which was first proposed a while ago. And then this year we had our first experiment published. It's a tunable cavity where there's the TM mode and a TE mode, and the TM mode doesn't tune because it only depends on the radius, and the TE mode is tuned by the cavity height. We use a TM020 mode and a TE011 mode, and one tunes and one doesn't. And the student is Katrina Thompson, is the PhD student on that. We've also published in the past, we've done a lot of work with magnons interacting with photons. Graham is writing up his PhD on this. He's published a couple of papers. We first did this work as part of our quantum systems program, where we strongly coupled, we got very strong coupling with magnons and photons. Actually, probably the strongest you can get by using these special cavities, which it's not part of this talk. But this is all technology that seems now you can use for gravity waves. Yeah, we got a patent on that, and that was published in 2014. ADMX as well. This just came on the archive. We're working with ADMX now. We're part of that team. And Tatsumi was the driver of this paper, which is just on the archive a couple of days ago. And the interesting thing here is that we monitor 2 modes, one mode that is sensitive to axions and one that isn't. So if you get a candidate event, you can look in both modes and see if it's there or not. And probably that might be something you want to do in gravity waves too. Have one that's sensitive and one that isn't, if you really want to have a strong idea if your signal's gravity wave or not. Another interesting thing is ADMX actually has this Sidecar experiment, and there will be a new paper coming out soon. And that's where in their big ADMX cavity, they have this little sidecar. So I have about 3 meetings with the team every week. I've had 2 since this conference, and I've updated them on the conference, telling them how everyone's talking about their experiment. And so I said to them, Dave Tanner, who's a LIGO guy, is in those talks. And why not a high frequency gravity wave detector as a sidecar detector in organ or ADMX? It's possible because there's spare space, and maybe if you put in a gradient part of the magnetic field, you could get some sensitivity. And Chelsea Bartram is leading this paper at the moment, which should be on the archive soon, the new sidecar. So now resonant mass systems that we've worked on at UWA, we've worked on this for testing quantum gravity and high frequency gravity wave sources, because with the same sort of resonant detectors, you can put limits on the uncertainty principle as you have a macroscopic mass. So there's Bohr's, and we have this Sapphire resonator where it has an acoustic modes and also electromagnetic modes, and it's a parametric effect where it's not a parametric effect in the quartz pores, it's a linear effect. I'll make that more clearer later. But we did this limits on quantum gravity with the Bohr and the sapphire, and both of those could be used for gravity waves. And this is Jeremy, who's now a postdoc with us after a postdoc in France. He's come back to work with us. This was his PhD and was on this resonator where you were to get acoustic modes and Springari modes, and the strain dependence of permittivity would modulate the microwaves in that bar. We've also, this is dumbbell shape, we've also looked at straight bars as well. So now a brief history of what I say is the nearly extinct resonant mass detector, which is making a comeback. There was Weber's pioneering work, and in his pioneering work, he's talked about bars, spheres, and torsional detectors are possible. We call these resonant mass. This will be a resonant bar, a resonant sphere, a resonant torsional detector. But if you want to lump them all together, we say resonant mass. That was the terminology. And Weber actually proposed using piezoelectric crystals like quartz to detect gravity waves at 10 to the 7 hertz. So we're actually following his suggestion, which is what I realized when I looked over his papers. I met him once and I really loved talking to him. He was full of stories. And I'm very pleased to know that we're following one of his suggestions. This was my PhD back in 1989 to 93, which probably reveals how old I am, but where I worked on this parametric transducer. Back in those days, there was a network of these detectors and which were looking for gravity waves. We were Niobe, there was Nautilus, Auriga, Explorer, Allegro, and there's also a sphere in Sao Paulo. Here's a picture of Niobe, Explorer, Auriga, and the Mario Schoenberg detector in Sao Paulo. I did a little bit of work with that group, which was quite fun. Now our detector was the 1.5 tons. Fundamental resonance was 10 to the 8 with 700 hertz. It would take 1 day to ring down. So if we excited it by accident, we couldn't catch it with our transducer and we'd have to wait for it to, we couldn't damp it to start experiments again. These things are very big, so they're very low displacement. So the impedance matching is bad. So you used to put in another resonant mass to integrate the transducer in those days. We achieved first operation of a detector with parametric cooling. We didn't call it cooling in those days. We called it cold damping in the bad cavity limit. It's because it gets cold and damp. So I don't like the term cooling because some people get misled and don't realize the Q goes down as well. Q on T remains constant. I have seen talks more recently where people thought they could get better signal to noise by doing this type of cooling. With the Sapphire transducer, we actually did the first ever resolved sideband cooling on a macroscopic mass. That was in the 90s, but no one used that language then. We just called it cold damping in the limit where you could do QND. We saw all these parametric effects and we damped the modes of our detector. When we looked at the sensitivity of the noise temperature on Q, it should be constant as you increase the power. And then we get extra because of back action. So when you're doing these type of experiments, you've got to be careful of back action. And if it's a parametric system where you're pumping in photons, the amplitude noise will add noise to your system. So you've got to be careful of the photons and the noise on them. In general, there are 2 transducer concepts. One is parametric, which is now called optomechanics. Even if it's microwave, I always found that amusing because there's nothing optical, it's microwaves. But it's what you would call that optomechanics now. And Niobe was of this type, and so was Mario Schoenberg. All the rest were direct, which we call direct and use squids. And so they would use a pancake coil and a transformer to impedance match to the squid because their bar to get a better transfer of energy. In the quartz Bohr is sort of like this, except we don't need this part. The quartz bore does not need the pickup coil that were used in the old and a transformer for impedance matching. It just needs this part directly to, and that's what is a sort of useful about the quartz. This signal is detected as a modulation of the pump, and the critical requirements are low pump. You've got to have a low noise source, a low noise amplifier at the modulation frequency of your carrier. This one gives you a direct signal at the antenna frequency. You need a low noise squared amplifier and low mechanical loss circuitry, something that doesn't add loss or parasitic resonances. So what you would do is, in those days, we would have two modes, but there would be your resonance system, there's a transducer, then an amplifier, and you could read out the two quadratures. If it's high Q, and one of the important parameters is the electromechanical coupling. And so what you do is you measure these quadratures, and the gravity waves changes the state of motion. So it's undergoing a random walk in phase space, and then you'll get a kick, which you can measure by applying a filter. So we had these filter techniques with some optimal filter. You'd get your gravity wave comes in here. You've got some noise coming in here. It sees the transfer function. Then you've got noise coming in here, and you get your two quadratures in lock-in amplifier, and you'll get this amplitude, hopefully just excited by thermal noise, walking around, and then you can get the mode temperature by doing a histogram. We were working in the cold damp regime, which should have been 4 Kelvin, but we were actually 367 millikelvin mode temperature because we were damping in it by our parametric transducer by a factor of 13. So the noise temperature was lowest, but so was the Q. It was no longer 10 to the 8. It was an order of magnitude lower, 10 to the 7. And when you look at the difference here, your noise temperature is much smaller. So that's how sensitive you are. And here you get much better because of your high Q, and you're just measuring a change in the state. And you would have narrow band and low, and so if you used a 0 order predictor filter, you would use a sampling time which would balance your narrow band and broadband noise. Narrow band noise comes, any input from here will excite a Lorentzian. That'll be narrow band noise at the output. Any noise at there would be broadband. We used this sapphire transducer as well. And we did some fun things, but I won't go into that. We've got to be careful of the noise sources. You must consider them more. You have narrowband noise, which is your thermal Nyquist noise and back action, and you have series noise. And so you have balancing broadband noise with narrowband noise in your system. You have back action noise due to the amplitude modulations of your carrier, and your pump phase noise is also a problem because it can give you. Then you have the noise in your first amplifier system. These are when you're doing a real experiment or all important parameters. Now there's a spectral strain sensitivity. If I had one mass, a resonant bar is actually a broadband detector. People get the idea that it's a narrowband detector. So you have if this is just one mass 1, and we only had the gravity wave and the thermal noise and no other noise source, you could measure your signal to noise ratio would be constant across the whole frequency range. Of course, you have other modes, and that's not true. If you have a low mass, you don't really need to put a second mass, but in the big bars, we'll put a second mass so you could impedance match to your transducer. And so if you had 2 masses, your thermal noise would look like that. When you put the transducer on, the noise comes here, and your transducer noise now looks like this. This is in strain sensitivity per root hertz, actually. So you're referring all your noise back to the strain of the gravity wave. And so all your noise sources in terms of spectral strain sensitivity. Signal to noise ratio looks like this. If we improve the transducer, we get a bigger bandwidth. If we pull this transducer noise down, our bandwidth gets bigger. And you can get very large bandwidths with these type of systems. Here is exactly Allegro noise theory and experiment showing exactly these curves. So what signals can we detect with a resonant detector? A burst detection will use the total bandwidth. A search for pulsars will look for the minimum here. And stochastic, you need 2 detectors with coincident spectral, same low spectral noise. Improving this, so if you improve the sensitivity by improved transducers, we did some modeling and showed how wide a bandwidth you could get if you went, this was our detector before it went offline, and this is if we got to very, improved our transducer, went to millikelvin. So now we get finally to the bulk, to the quartz resonators, because this is a resonant detector and it's the same sort of thing. Bores are 5 to 10 megahertz at room temperature, QF equals constant. When they go to low temperatures, the physics is different. They're small, about I don't know, 10 millimeters across. And the best is BBA technology. It looks like this. It's the acoustic equivalent to a Fabry-Perot cavity for phonons. And you can have a frequency range of about 1 megahertz to a gigahertz. We looked at low temperature properties and got very high Qs. Our best was 8 billion at about 4 Kelvin. And we observed some new loss mechanisms like the the equivalent of Rayleigh scattering for phonons. And this is the sort of properties as you go to low temperatures, 3.8, 15 millikelvin, you've got a Rayleigh scattering part. You can even get below 4K down to 10 to the 10.
Oh, 5 minutes?
Yes. So, well, yes, okay. So we use this squid technology. We can calibrate it and by measuring the transimpedance. I won't get into the boring details. And we can calculate the mode temperature. And we did that with a range of experiments. And our mode temperature was equal to the physical temperature. When we went to 50 millikelvin, the squid wasn't made for that, so it didn't work so well. But we got some millikelvin squids now, so we can do that in the future. But what we showed is our mode temperature in the quartz core was equal to the physical temperature, and that is what you want. Now the high frequency gravity waves, we then in this paper, we showed what the sensitivity you could get. We worked out all the physics. And in our recent paper, we saw some events which has recently been published. This is the experiment. It uses control and signal processing with 2 modes with a lock-in amplifier. These are the squids, and we do digital down conversion. It is very well shielded. All it is a resonator with a squid, with a niobium shield around the squid, a copper shield around the quartz, and another niobium shield, well shielded, and then an amplifier, room temperature amplifier. So you should see nothing. And we left it running for 153 days. You get a histogram and you see some high energy events out here. We saw one event here. We actually saw a third event, but Seong told us this wasn't significant enough. He was the expert, so we never reported it. It signaled to him, it just wasn't significant enough. If you look at these modes, this is the histogram for the whole data runs. And this is the histogram just around this event. And you can see all the high energy events are due to this event. That's what this shows. And here again, the whole run, and you can see they're pretty much overlap. So all the outliers were due to these 2 events. This is the thermal noise that you see. It's demodulated, so it's not exactly at megahertz. This is just the offset frequency. And when you put it up to megahertz, this is by 10 to the 6, you can see where we're sensitive in a very narrow band. And if you expand it out, this is in hertz, you can see the strain sensitivity curves as we've seen in the resonant detector, we can calculate. So now I will, in the last of it, we're going to introduce our new experiment. So we thought we had to give our new experiment a name. It's called Multi-Mode Acoustic Gravitational Wave Experiment, MAGE. And that's the icon. You can see a quartz up here. And our new experiment is going to use multi-devices and multi-modes and use FPGA digitizers. We're going to have, also we're going to look for cosmic rays at the same time. So this is the main goals of our new experiment. 2 identical quartz resonators currently, maybe more if our discovery application gets up. It's going to be multi-mode, multi-detector, monitoring with the FPGA. And we're going to have a high number of modes. 8 to 10 modes, 5 to 15 megahertz per crystal. And with wider bandwidth squid, we can go up to 200 megahertz. We're going to have a cosmic particle veto system, which is potentially cryogenic. And we're going to have sub-Kelvin operation in the future, which could become quantum limited and have higher Qs. And you could get into a regime where you could do quantum metrology. We're going to think about larger masses and optimum size and mode sensitivity. We haven't really optimized this. We've just used the devices we've had because they've been designed for 5 megahertz. Current status of this major experiment is that we're waiting for the second FPGA. We've only got one. We've already collected 1 week's of data of monitoring 8 modes of Bohr 1. So that's just sitting there and we haven't looked at it. So that's the end. And hopefully I didn't go too much over time and I can take questions.
Actually, the timing was perfect. Thank you very much. Are there questions for Micheal Tobar? Valerie, please go ahead.
Thank you. Yeah, thanks for the great talk. I actually have many questions, but because you covered a lot of stuff. But maybe, okay, let me ask first on your very first part, the Axion technology. So do you actually like have any, or did anybody put any gravitational waves limits from any of the things that you proposed, or these are kind of still ideas?
No, we haven't done anything on gravity waves without Axion detectors. What we've done is we've written a grant and proposed to do it. And if we get funded, we will. What we'll do is we'll put a sidecar in this experiment. I have a hunch that you'll want a gravity gradient in these experiments, but I'm not sure if that's right. I just have a hunch. I've thought about it the last couple of days since the talks, and I do have some questions on these type of experiments.
Thank you.
Okay, Juan, you have a question?
Yes, actually, I thought it was a beautiful talk. Thank you, Micheal. I wanted to ask you about your ability to detect stochastic backgrounds. So in principle, I understand that you can detect a single event very clearly, but what about stochastic backgrounds? Can you monitor your detector for long enough? And do you gain by integrating over time? And what would be the typical amplitude that you might be able to get?
Yeah, well, I'm not an expert on sources, but Sion's a sort of expert on doing the data analysis. But the problem is we need to get 2 Bohrs at the same frequency. And they're very high Q and they're very hard to get at the same frequency. And we haven't been able to achieve that. They're close in frequency, but they're not at the same frequency. We had a problem with, we were using them for scalar, we can use them for scalar dark matter as well, but the problem is our line widths are more narrow than the actual dark matter. So what do you do then? You can't even measure it because the Q is too good.
Right, I see. Yeah, something similar with the gravitational background. Yeah.
Yeah.
Okay. So do you envision having another experiment? I mean, another setup similar to this, but at some distance? You could send it to the other side of the country.
Yeah, so we will do it in the lab. It depends on the coherence length, I think. Or well, if it's an event, yeah, you can, maybe it's, you see it in both, depending on the, I don't know what the wave fronts look like at megahertz. I have no idea. Theorists will know better than me. Theorists can tell me where we should put them. But we already got a friend, Pavel Bushriff in Germany, who wants to build one. So.
Oh, great. Good to hear. Thanks.
More questions? Fernando Quevedo, please.
Yes. Yeah, very nice talk. In your new proposal, what would be the frequency range and sensitivities?
Aha. Our new proposal is to try and just detect more to understand what these events are. So they're pretty much the same sensitivity as we have, except we're measuring more modes and we have more than one detector so we can correlate. When we did the resonant bars, if we were ever going to make a detection, we knew we needed at least 3 detectors to get a coincidence. because they're narrow band, and you need to, once you correlate the signals coming in, if you have 2, the probability of detection of it being a false detection goes way down, but still finite. If you have 3, then you can be sure. So my goal would be have 3, and maybe even more, to have 6 detectors in the lab, so you could look at different directions as well.
Okay. Okay. Thank you.
Okay, so let's then continue with the next speaker.